It is easy to get carried away with a new technology. It is just so much fun to play around with it. I know I've lost countless hours doing exactly the same thing. It's compelling, but it doesn't help us create the vision of the future. And that's why we have to really structure our empirical research. I'm Chris Woods. This is the Industrial Research Podcast. And this is our last episode in our mini-series on the research roadmap process. I have to apologise for it being delayed. A lot of things have happened. We've had sick kids and boiler rooms that have exploded in water, dehumidifiers, and my recording studio here in the basement has turned into a very large fan. Not great for recording podcasts, but we're back, firing on all cylinders now. In our previous episodes, we have covered an awful lot of detail. We covered the research roadmap process first phase about creating that vision of the future and how global trends really help us to predict what might happen. Then we looked at the second phase, which was about taking that vision of the future and breaking out those questions. What do we need to solve? What problems do we need to overcome to make that vision a reality? And those problems fall into one of three different categories. They're either problems where we've already solved them, or somebody else has solved them and we don't need to worry about it. Or they're problems where we know that there are more than one solution available to address them. Or it's a problem where we don't have a clue how to solve it and we might need to create new technology. And in this podcast, what I really want to go through is how we address those three different situations. But I also want to cover this really important point of how not to get distracted. Keeping focused on what we need to do is essential. And getting distracted in new research papers, new concepts, new types and approaches of ideas, in new problems. It's such a big deal, and it affects so many of us that there are even people who've written papers to try and address that. And one of them is this guy called Dr. Peyton Jones. Now, Dr. Peyton Jones is a researcher with Microsoft Research based in Cambridge in the UK. And he has this slide deck, which if you check out my notes accompanying this podcast, you'll see a link to it. He has this slide deck and it's great. He talks about how to structure your research. And his basic proposal is to structure your research as if it's a scientific paper. So he goes through that process of setting out a problem, doing your fundamental research, and identifying the key questions you're going to address and what you're going to do about it, your hypothesis, and whether or not your hypothesis is true or false, and the experiments you did to try and address that. And that basic structure is the structure of an academic paper. And he goes through that in detail and he shows you how you can think about writing the paper. Most researchers, we would all go, let's go and solve the problem or research the problem, get a solution, then write it up in a paper. And what Dr. Peyton Jones is suggesting is, let's flip that. Let's write the paper as we're doing the work. And what that does is it keeps us focused because we're doing it in this methodical step-by-step approach, which is what's my problem space? What's the background reading in that problem space? What ideas can I come up with to address those problems, and how can I test them? And that methodic approach helps to keep us focused. Now, for those of us who aren't from the academic background and don't know much about these papers, research papers are published by researchers around the world and usually peer-reviewed and published in journals. Now, some organizations use them as a measure of success. The number of papers a researcher's got published is one metric. The other metric is the number of citations, and that's where another researcher has cited your paper as inspiring their paper or providing a data or a proof point for their paper going forward. And that's also used as a measurement of success. So much so that some government agencies actually use it. So in Ireland, the Science Foundation Ireland, which is a government body that helps structure and fund academic research in the Republic of Ireland, they use that as a measure of success for some of their investments. So I attended a presentation once where the head of the SFI, Science Foundation Ireland, was showing the number of academic papers in computer science published by Irish researchers from the Republic of Ireland and the number of citations that they had gotten or achieved. So it's a big thing. So if we follow this process, we get to keep ourselves really focused. Now we've actually got to go on and do the real research. So we've identified our problem from our vision of the future. The next stage is working out what technologies might fit that. And when we have a situation where we have multiple technologies that fit a problem space, we have to work out how and why we create those experiments to test them. The first thing I think is to really understand where these technologies have come from. And then the second thing to think about is what metrics are really important to address your problem that you've identified in your scenario. So when we think about where these technologies have come from, very often they've come from adjacent technology fields, where they've been designed with those technology fields' unique requirements in mind. And those requirements will be different from ours. They may be similar, but they won't be an exact match. And this helps explain why we have this difference in performance behavior or difference in performance requirements. So for instance, as a quick example, there's a body in the US called the Advanced Robotic Manufacturing, ARM, and they sponsor a lot of research, and they were looking at network protocols. There's network protocols for factory automation that exist today, and they perform a certain way. And there's a second set of network protocols that they were evaluating, and they came from a wide range of different fields, from the web, for instance, or from the more military side. And they all perform in a slightly different way, with different characteristics, different performance characteristics. So using a web-based API that you might use to post a tweet to Twitter or a post to Facebook or to download some web content, that job has a different set of performance characteristics to what we might need to control a robot on a factory floor. Understanding where these other technologies have originated and why helps us understand and try to anticipate how they might behave in our scenario, and gives us a little bit of a heads up on how we might need to design our experiment. To really design the experiment, though, we've got to know what we're looking for, what those core KPIs or performance metrics or behaviors that we're really interested in. And to understand those, we've got to go back again to our scenario. So when we came up with our questions about a vision of the future, we took them and then we derived them from this scenario, this written scenario. Sometimes those scenarios won't have all the detail we need. And let me give you an example. Let's suppose that we are designing a temperature sensor that needs to be placed in a consumer's home. We want them to take it home, connect it to the Wi-Fi network, and then have it just work. And I'm really familiar with that because many of us have Amazon Alexas, and mine's just lit up in the corner of the room, or Google Homes, or the Apple equivalent, and setting those up is basically the same thing, connected to the internet, and it just works. But let's suppose that we want our temperature sensor to behave in a different way. Normally, our Alexas, he says cautiously, looking at the light glowing in the background, our Alexas will connect to an Amazon server, and they will call out to the Amazon server and maintain this open connection the whole time. But let's say that we don't want to do that. Let's say that we want our temperature sensor to sit in our house and we want the cloud to be able to call it. Now this introduces a whole bunch of problems. How do you do that? Normally that temperature sensor will sit behind your home's firewall that you're network service provider gives you in your router. You've got to get past that to talk to it. There are a whole bunch of software solutions to try and address this. But when we think about them, it opens up this Pandora's box of additional questions. Like, we could solve it, but what would the load be on the cloud server? Or how much additional data would we transfer? Or what would the latency, which is the time it takes from the cloud asking to talk to the sensor and for the sensor to reply? And what is our good put? Our good put is the amount of application specific, in our case it's temperature data specific, data information that's passed over the network. How do we know which of those properties are really important? Well, the truth is we don't. We've got to go back to our scenario and dig them out and really understand what that scenario is trying to deliver. So that will require us to go back and maybe talk to a business unit to get some more information about a scenario, or talk to a product manager about what a future product should do, and try and really drill down to pull out those core metrics. And that's what allows us to have a benchmark on what's really important. So maybe the load in the cloud server for us might not be important, but the latency might be. And it all depends on what the application is. I mean, if this is a temperature sensor sitting in a home, arguably the temperature doesn't change that dramatically. So maybe latency isn't that important. But if it's a temperature sensor in an industrial world where the temperature can change quite dramatically, quite vigorously, and we need to know exactly when those temperature changes occur, or we need to be able to call on it at a moment's notice to get the latest information, well then latency is an issue, and we have to be able to talk to that sensor very, very quickly. So all this leads into our experiment design, and we've got to kind of nail down how we're going to do it. Now, for our temperature sensor example, there's a whole bunch of open source networking software and protocols available for us to use. And this leads on to the next really important question. Quite aside from the technical requirements, when we're deciding which technologies to use, we also have to consider the business requirements. And that allows us to filter some of those ideas and some of those concepts and some of the open source software packages we're dealing with straight away. If we're recommending a technology to our employer and we're saying, hey boss, I think you should really use this in your latest product, that could very well be a multi-million dollar, multi-million euro, pound effort. And that's a big risk. Ultimately, we are betting our future jobs and our own livelihood and the livelihood of our company on this technology. So we want to be sure that it's good and it's going to be around for a while. So most organizations will try and qualify that risk, and they will ask questions about any open source software or project that you want to use. Questions like, how long has that project been running for? Are there other organizations that are already using it? Has it been commercially deployed already? And who maintains it? And what is the frequency of the updates? For well-established projects, and we can think of things like Kubernetes, which is a cloud orchestration framework that has been around for a long time and sponsored by Google, maintained by Google predominantly, then that has a pretty good pedigree, and we can be pretty safe in taking that technology. But we think of more emerging technologies, then that the infrastructure of a supporting organization might not be there yet. It might not have the critical mass that we need. And it can sometimes feel like this is an unfair thing. It points the organization towards pre-existing and already successful projects. But if you can make the case for those newer projects that don't have that existing support structure, then your organization might take those up too. But they might want to take on the role of being a maintainer or nominate a staff member. Because remember, the cost of using any piece of software isn't just the cost of writing it, but the cost of writing it and maintaining it for the lifetime of its use. So if we're embedding this software in something like a temperature sensor, which we want to sell, and we want to keep this temperature sensor running for 10 years, 15 years, 20 years, we're going to need to maintain that software that's running on there. Make sure it can't be hacked. Make sure it's supporting the latest Wi-Fi connection types. It can talk to our servers if there's any changes to what happens on those servers. There's a lot of work just in making the status quo stick. And it's a cost. And we just have to bear that in mind. And this leads nicely on to creating a new technology solution. My background is as a software developer. And, when I first graduated, all I ever wanted to do was write software and create stuff. Yeah, let's go write it. Even if it had been solved already before, just the thrill of writing it yourself was compelling and you wanted to do it. Well, I wanted to do it. And that wasn't until I found myself at an operating system company at Symbian. And I was looking at Wi-Fi APIs. I had the chance to help design them and change some of them. And I wanted to introduce some new functions that would allow third-party applications to do things easier. And the answer that came back was, do you understand the cost of those? You write one new function. It's just not one new function. It's that function, that signature with its calling pattern that you have to maintain today and next year and for the next 5-10 years time. And that's a huge cost. So we don't add new functions and new APIs unless we really have to, unless there's a really compelling reason for it, because we have to maintain it and that costs money. So when you come to the conclusion that there is no viable other solution, my first bit of advice is to go back, search, and search again. If we've come to that conclusion, it implies that we have already done our homework and we've looked at all of the alternative solutions. And just go back and double check. If you've looked at academic papers, try posting to some forums, talk to colleagues. Just make sure you really nail this, because if we're going to go down this path, there is a cost. So make sure you've done your homework. And then, before creating it, my single most important tip is make sure you have nailed your specification. Understand exactly what it has to do. And this is basically the same question as this multiple technology evaluation. Sometimes we'll conclude that we need a new piece of software. We have to write this. Nobody else has done it before. But it's based on this vague open question from a scenario. And it's not pushed and locked down to say it must perform at this rate. Our temperature sensor must be able to talk within 500 milliseconds latency of the server. We haven't got that level of detail. And it means that if we create a new piece of technology, in my case software, we need to be able to evaluate this new technology against the criteria. How close are we to our goal? Could we improve it? Is the design good enough to stop? Do we need to keep going? Ultimately, as we go to create new software or new technologies, we might reach the conclusion that we can't solve this problem. It's just not possible today. And that's okay too. That's a good finding. It might be worthwhile shelving and mothballing that research. And that's why taking this paper writing approach that Peyton Jones talks about is so important. Because even if your research and your search and your attempt to create a new piece of software or a new technology doesn't work, you can still record how far you got. And you've got a paper that tells you, I got this far. These were the limiting factors. I cannot go any further. This all brings us back to the research roadmap. Having the results is important. We've done our research. We've evaluated multiple technologies. We got some results out of that. We tried to create some new technology. Maybe we've got some results out of that. Maybe it worked. Maybe it didn't. Maybe those multiple technologies we evaluated, none were a good candidate. This all seems like bad news, but it's important data. We take all of that information and we go back to a research roadmap process. And anybody who's had a look at some of the previous blog posts on this, you'll have seen the research roadmap process all drawn up. And there's a final loop that loops the empirical research back to the vision of the future. And we take all of that data, everything we've learned, and we go back to the vision of the future and we start to update it. We say, I can't create a technology for this. It doesn't fit yet. I haven't got a fast enough processor. Maybe Wi-Fi is not good enough, or maybe there's just not enough RAM in a computer, or whatever the problem happens to be. And we say, this path won't work today. Therefore, we need to look at either an alternative vision of the future, or we need to update that vision and show a different implementation path to achieve it. And that's another piece of research. So this is how the whole thing kind of links up and comes together. We have covered an awful lot in this little mini-series, from looking at research and where it comes from and structuring that research, looking at the research roadmap and the 3 phases and how we link everything together. And I hope you found this really useful. This is the last episode of this mini-series on the research roadmap process. I hope to do more in the future. And if you've got any ideas or questions or suggestions, please get in touch and let me know. You can find me on Twitter as @MCWoods. You can even find me on LinkedIn. And if you check the show notes and go to the blog post that it links to, you'll see a text version of this episode, complete with links to everything that you need. And if you want to, my LinkedIn profile to reach me there. Stay safe. Things are looking up, touch wood, on the whole COVID stuff, and hopefully normality will resume in some way, shape or form in the not too distant future. In the meantime, stay safe, take care, and I look forward to talking to you in the next series. The music used is an excerpt from Bust This, Bust That by Professor Cleek and is used under Creative Commons.